Imagine a world where cars drive themselves. No steering wheel, no pedals, just a sleek, intelligent machine that gets you from point A to point B while you relax, read, or even sleep. This is the promise of self-driving cars, a vision that has captivated the imaginations of technologists, automakers, and futurists for decades. Self-driving cars, or autonomous vehicles, AVs, represent a profound shift in how we think about transportation. They have the potential to make roads safer, reduce traffic congestion, increase mobility for the elderly and disabled, and revolutionize urban planning. However, creating a self-driving car is not just about programming a vehicle to follow a map. It involves replicating the complex decision-making capabilities of a human driver, a monumental challenge that requires a deep integration of cutting-edge technologies. Driving involves a constant flow of decisions based on a wide range of sensory inputs: the speed and distance of nearby vehicles, road signs, lane markings, the behavior of pedestrians, changing weather conditions, and more. Replicating this in a machine is no simple feat. The quest for autonomy in vehicles is about more than just removing the driver. It's about creating a vehicle that can perceive its environment, understand what it sees, make decisions, and act on those decisions, all in real time. This requires a combination of hardware and software, sensors and algorithms, and an intricate dance between data and action. To better understand how self-driving cars are being developed, let's first look at how they see the world around them. Chapter 2: Eyes on the Road. For a self-driving car to navigate safely, it needs to perceive its environment accurately. Unlike human drivers who rely on eyes and ears, autonomous vehicles use a suite of advanced sensors to achieve a comprehensive 360-degree view of their surroundings. These sensors work together to detect obstacles, recognize traffic signs, track pedestrians, and identify other vehicles. Each type of sensor has its strengths and limitations, and they must work in unison to provide a reliable picture of the world. Cameras are one of the primary sensors used in self-driving cars. They are capable of capturing high-resolution images of the environment, which are essential for detecting and classifying objects such as traffic signs, lane markings, pedestrians, and other vehicles. Cameras provide color information, which is useful for understanding traffic lights and other visual cues. However, cameras alone have limitations. They can be affected by poor lighting conditions, glare from the sun, or heavy rain, which can obscure their view. LiDAR, light detection and ranging, is another critical sensor technology in self-driving cars. LiDAR uses laser beams to measure distances by bouncing light off objects and calculating the time it takes for the light to return. This process generates a precise, three-dimensional map of the surroundings. LiDAR is highly accurate and can detect objects at a distance, making it ideal for identifying obstacles, even in low-light conditions. However, LiDAR systems can be expensive and their performance can degrade in adverse weather conditions such as heavy rain or fog. Radar, radio detection and ranging, is a sensor technology that uses radio waves to detect objects and measure their speed and distance. Radar is particularly effective in detecting larger objects, such as vehicles, and works well in all weather conditions. It can see through rain, snow, and fog, providing an additional layer of reliability. Radar systems are essential for understanding the relative speed of surrounding vehicles, which is crucial for tasks like adaptive cruise control and collision avoidance. Ultrasonic sensors are used for close-range detection. These sensors emit sound waves and measure the time it takes for the waves to bounce back after hitting an object. Ultrasonic sensors are commonly used for low-speed maneuvers, such as parking and avoiding obstacles in tight spaces. They provide precise distance measurements at short ranges, but are less effective at higher speeds or longer distances. Individually, each sensor has its limitations, but when combined, they provide a comprehensive understanding of the environment. This is known as sensor fusion. Sensor fusion integrates data from cameras, LiDAR, radar, and ultrasonic sensors to create a detailed, real-time 3D map of the vehicle's surroundings. This map allows the car to see and understand its environment with a high degree of accuracy. Redundancy is built into the system, ensuring that if one sensor fails or provides inaccurate data, others can compensate to maintain a reliable picture of the road ahead. By combining multiple types of sensors, self-driving cars can perceive their environment more robustly and reliably, reducing the likelihood of errors and improving safety. But seeing is just the first step. The real challenge lies in making sense of this information and deciding how to act on it. Chapter 3: Making Sense of the World. The vast amounts of raw data collected by a self-driving car's sensors are meaningless without a way to interpret them. This is where perception comes in, the process of turning raw sensor data into meaningful information about the world. For a car to drive autonomously, it must understand what it sees. It needs to recognize and classify objects such as other vehicles, pedestrians, traffic signs, cyclists, and lane markings. Perception in self-driving cars relies heavily on machine learning and deep neural networks. These technologies enable the car to learn from vast datasets and improve its understanding of different driving scenarios. For example, a deep neural network can be trained to recognize pedestrians by analyzing thousands of images of people walking, running, or standing still in various conditions. Over time, the network learns to identify patterns and make accurate predictions. Deep learning models in autonomous vehicles are designed to perform object detection and object classification. Object detection involves identifying the location of objects within the car's field of view, while object classification involves determining what those objects are, whether they are vehicles, pedestrians, traffic lights, road signs, or any other relevant item. These models are constantly being refined and retrained with new data to improve their accuracy and robustness. But perception is not just about recognizing individual objects. It also involves scene understanding, the ability to comprehend the overall context of a situation. For instance, a car approaching a busy intersection must not only detect the vehicles and pedestrians around it, but also understand the dynamics of the scene. It needs to predict the actions of other road users, such as whether a pedestrian is about to step into the street or if another vehicle is likely to turn left. This requires sophisticated algorithms that can interpret complex environments and make real-time decisions. The ultimate goal of perception is to provide the self-driving car with a detailed understanding of its surroundings so it can safely navigate through them. But knowing where things are and what they are is not enough. The car also needs to know where it is and where it's going. Chapter 4: Plotting the Course. To drive autonomously, a self-driving car must know its precise location on the road and build a detailed map of its environment. This process is known as localization and mapping. Unlike human drivers who rely on landmarks, road signs, and a general sense of direction, autonomous vehicles require a far more precise understanding of their position. GPS, Global Positioning System, provides a basic level of location data, but it is not accurate enough on its own. GPS signals can be disrupted or blocked by tall buildings, tunnels, or other environmental factors, leading to errors that could be disastrous for a self-driving car. To achieve the necessary precision, self-driving cars use a combination of GPS and SLAM, simultaneous localization and mapping techniques. SLAM enables a vehicle to build a map of its environment while simultaneously determining its location within that map. This is done using sensor data from cameras, LiDAR, and radar to identify landmarks and features in the surroundings. The car continuously updates its map as it moves, allowing it to adapt to changes in the environment, such as new construction or road closures. Another critical component of localization is the use of high-definition HD maps. Unlike conventional maps used in everyday navigation apps, HD maps are incredibly detailed, providing information about lane boundaries, traffic lights, crosswalks, and even the height of the curb. These maps are accurate to within a few centimeters and are regularly updated to reflect changes in the road network. They serve as a reference for the vehicle's localization algorithms, helping it to stay precisely within its lane and follow the correct path. The fusion of GPS, SLAM, and HD maps allows self-driving cars to achieve high levels of accuracy and localization, ensuring they know exactly where they are at all times. This is crucial for safe navigation, especially in complex urban environments where precision is key. Chapter 5: The Driving Force. With a clear understanding of its environment and its precise location within it, the self-driving car is ready to navigate. This is where path planning and decision-making algorithms come into play. These algorithms determine the best route for the vehicle to take and how it should respond to dynamic situations on the road. Path planning involves generating a safe and efficient route for the car to follow. It takes into account various factors such as traffic rules, speed limits, road conditions, and the behavior of other road users. The car's AI system evaluates multiple possible paths and selects the one that minimizes risks and maximizes efficiency. For example, if a car is approaching a red light, the path planning algorithm will calculate the optimal speed for a smooth stop while avoiding abrupt braking. Decision-making is the process of determining the car's actions in real time. This could involve making decisions about lane changes, overtaking slower vehicles, navigating through intersections, or avoiding obstacles. The AI system continuously monitors the environment and updates its decisions based on new information. For instance, if a pedestrian suddenly steps into the road, the car must decide whether to brake, swerve, or take another action to avoid a collision. These decisions are governed by a combination of rule-based systems and machine learning models. Rule-based systems ensure that the car adheres to traffic laws and safety protocols, while machine learning models provide flexibility by allowing the car to learn from experience and adapt to new situations. Together, these algorithms enable the car to navigate safely and efficiently, mimicking the decision-making process of a human driver, but with greater precision and consistency. Chapter 6. Controlling the machine. Once the path is planned and decisions are made, the self-driving car needs to translate those decisions into real-world actions. This is where vehicle control systems come in. The control system is responsible for executing commands related to steering, acceleration, and braking. It must do so with high precision to ensure a smooth and safe ride. Control systems in autonomous vehicles are typically based on feedback loops that continuously monitor the car's position, speed, and direction. The system adjusts the vehicle's movements based on this feedback, ensuring that it stays on the planned path. For example, if the car starts to drift slightly out of its lane, the control system will make minor adjustments to the steering to keep it centered. The challenge lies in making these adjustments smoothly and reliably, especially at high speeds or in complex environments. The car must be able to perform a wide range of maneuvers, from sharp turns and sudden stops to smooth lane changes and precise parking. This requires advanced control algorithms that can handle the dynamics of the vehicle and ensure stability under all conditions. Safety is paramount, and control systems are designed with multiple layers of redundancy and fail-safes to ensure reliable operation. If a critical component fails, backup systems can take over to prevent accidents. This redundancy is a key aspect of making self-driving cars safe and trustworthy for widespread use. Chapter 7. The human element. While self-driving cars are designed to operate autonomously, they must also interact with humans, both inside and outside the vehicle. This raises important questions about human-machine interaction and the need for clear communication between autonomous vehicles, human drivers, and pedestrians. One of the key challenges is ensuring that people understand the intentions of self-driving cars. For example, how does a pedestrian know when it is safe to cross in front of a self-driving car? To address this, researchers are developing external communication systems such as LED displays, auditory signals, and even gestures to convey the car's intentions. These systems help bridge the gap between human intuition and machine logic, making interactions smoother and safer. Inside the vehicle, user interfaces play a crucial role in keeping passengers informed and engaged. For instance, a display might show the car's planned route, upcoming maneuvers, or alerts if the car needs to return control to the human driver. The goal is to create a comfortable and intuitive experience that builds trust and confidence in the technology. Chapter 8. The future of driving. As we look to the future, self-driving technology is on the brink of transforming transportation as we know it. The benefits are clear: fewer accidents, reduced traffic congestion, increased mobility for those who cannot drive, and more efficient use of time during commutes. However, the path to fully autonomous vehicles is still filled with challenges. Key hurdles remain, such as improving performance in adverse weather conditions, handling complex edge cases, and gaining public trust. Regulatory frameworks and ethical guidelines must also be established to ensure safe and equitable deployment of autonomous vehicles. The transition from human-driven to fully autonomous vehicles will likely be gradual, starting with advanced driver assistance systems, ADAS, and progressing to higher levels of autonomy. Despite these challenges, the momentum behind self-driving technology is undeniable. The progress made in recent years has been remarkable, and the potential impact on society is profound. As we move forward, we must balance innovation with responsibility, ensuring that self-driving cars are not only a marvel of technology, but also a force for good in our communities. The future of driving is coming, and it's bringing with it a new era of mobility, safety, and convenience. So, buckle up and get ready because the road ahead is one of endless possibilities.